All right, hello everybody. Welcome back to Physics 425. I wanted to start today by just recalling the roadmap that we wrote out at the start of the last video. And so what we've done is we've done some quantum mechanics review. We'll probably do a little bit more today. And we developed our wave functions for a pair of identical particles, and that's where we kind of left off. And so what our plan for today is to deduce the Pauli exclusion principle, which will be very quick, and we'll use our wave functions for two identical particles that we developed last time. And then we'll write down the so-called distribution functions for fermions and bosons, and we'll discuss the concept of a Fermi energy. So that's the plan for today, and so we're trying to tick off some of these boxes on our roadmap. So let me just remind you of... let me find it. Let me remind you of the two wave functions that we had written down. And so first we had a symmetric wave function, and it was constructed using products of single particle wave functions, so the phi a x1 and phi b x2, and then we added to that another product of phi a x2 and phi b x1. So phi a x1 represents particle 1 in quantum state A, phi b x2 represents particle 2 in quantum state B, and then when we add to that the same wave functions but with the particles swapped, so now particle 2 is in state A and particle 1 is in state B. That was the symmetric wave function, because when we apply the particle exchange operator, we get the exact same wave function back. The anti-symmetric was similar. The only difference is the sign. So instead of adding the two parts, there's a difference. And so when we apply the exchange operator in this case, we get the same wave function back, but with a negative sign. Okay. And so what we want to do now is we want to think about what happens if our two particles are in the same state. So the question is, what if the two particles, particle 1 and particle 2, are in the same state, A is equal to B? So we'll start with the symmetric case. So what we do in the symmetric case is we just set A equals B, and then we get phi a x1, phi a x2 plus phi a x2 times phi a x1. And the result is, in this case, the symmetric wave function is just going to become equal to 2 phi a x1, phi b x2. So now we don't have state B. They're both in state A, and we have no problem. This is still going to satisfy the exchange operation, and there's no issues with this. In the anti-symmetric case, however, when we do this, I'll write out the details in this one. So we would have, just working with this expression, we'll just, wherever we see a B, we're going to replace it with an A. So phi a x1 and phi a x2 minus phi a x2, phi a x1. And this is just the difference between two terms that are identical, and we get 0. The wave function vanishes. So in this case, the wave function vanishes, And you know what the wave function does, if we take the absolute square, as we saw, it tells us the probability of finding our system in this configuration. And so if the wave function vanishes, there's zero probability of finding our two particles in the same state. So the anti-symmetric wave function does not allow two identical particles to occupy the same quantum state. This is kind of an elegant argument of a pretty profound principle, and so this is called the Pauli exclusion principle. It's very important for systems at low temperature because what we found is that for bosons we can put particles in the same state. There's no issue with that. And so if you went to really low temperatures, all of the bosons are going to try to occupy the lowest energy state. And in fact, we'll talk about Bose-Einstein condensation, which is a manifestation of that. In fermions, however, if you're at low temperatures, all you can do is you can put a single particle in the lowest state, and then no other particles can occupy that same quantum state. And so you have to start building, the next particle is going to go into the next lowest state, and so they start occupying higher and higher energy level states. Okay. So in nature, particles with integer spin, and so this is not something that I'm going to prove, I'm just going to state the fact. So these are particles with spin is 0, 1, 2, and so on, integer spin. So these particles have symmetric wave functions, and they are called bosons. So examples of bosons are photons, phonons. Phonons are vibrations in lattices. The helium-4 atom is going to be one that's relevant to us. So gluons and the nucleus and so on. Okay, and so we can have any number of identical bosons in the same quantum state. So there's something called the Bose-Einstein distribution function, and so I want to write that down. The Bose-Einstein distribution gives the average number of bosons in state with energy epsilon when the system is at a temperature T. And so we have a bunch of quantum states. They have different energies. We can specify that energy with epsilon. So at a given temperature, we use this Bose-Einstein distribution function to figure out the average number of particles in each of those states. And so we'll give this a symbol n bar for the average number of particles, the subscript Bose-Einstein. This distribution function, again, I'm not going to prove it. We hopefully will actually derive it later in the course. But it looks like this. E is the energy of the state, mu is the chemical potential, T is temperature. So let's think about some fixed temperature, and if we went to a very high energy. So if we went to a high energy epsilon, then e to a large number is going to be very large, and we have 1 divided by a large number minus 1. And so in this case, for large epsilon, the average number of particles in a quantum state, or the occupation number, goes to 0. And so we can try to plot this as a function of energy. The Bose-Einstein distribution function at high energies looks something like this. Okay, and so it turns out that this quantity epsilon minus mu for bosons can't go negative. And so that means it can approach 0. And so if we go to low energies, so that epsilon minus mu approaches 0, then we get e to the 0, which is 1, and in the denominator we get 1 minus 1, which is close to 0, and so we have 1 over something close to 0, or a very small number, and so this occupation number diverges. And so actually I'm going to try to redraw this a little bit. So at high energies we have very few particles in our system, and at low energies the number of particles in a state grows. Okay, and so that's the Bose-Einstein distribution. And so next we have fermions. In nature, particles with half integer spin. So it's going to be like 1/2, 3/2, 5/2, and so on. Have anti-symmetric wave functions and are called fermions. Okay, so examples of fermions are electrons of spin 1/2, quarks, protons, neutrons, and helium-3 atoms will be one that's of interest to us. Okay, so we can have only 0 or 1 identical fermion in the same quantum state. That is, our system must obey the Pauli exclusion principle that we just talked about. Exclusion principle. Okay, the distribution function, or the average number of particles in a state for fermions, is given by the Fermi-Dirac distribution, and it has a similar form. In fact, it's 1 over this exponential that involves chemical potential, the energy of the state, and temperature, and there's also a 1 in the denominator. For the Bose-Einstein distribution, we subtracted that 1, and for the Fermi-Dirac distribution, we're going to add that 1. And the sign in front of the 1 in the denominator has a big effect. Okay, so this Fermi-Dirac distribution gives the average number of fermions in a state with energy epsilon when the system temperature is T. Okay, so let's again try to plot this. So here's the energy, and here's the Fermi-Dirac distribution. So again, we could think of sitting at some fixed temperature, and we go to a very large energy. So e to the epsilon is going to be a large number. So we have 1 over a large number plus 1, and so that is, again, close to 0. So in fact, at very high energies, the system of fermions and bosons actually behave in a similar way. Now, for fermions, we'll see later that, in fact, in this exponential, the epsilon minus mu can become, it can be negative or positive or 0. So that's going to be another difference between our fermion and boson systems. So let's suppose that our chemical potential is sitting here along the energy axis. And so what happens when epsilon minus mu is 0? Well, in that case, we get e to the 0, which is 1. And so we have 1 plus 1 in the denominator, and the average number of particles in this state with energy mu becomes 1/2. So of course you can't have half a particle, but if you set up a bunch of identical systems and looked at them, half the time that state would be occupied and half the time it wouldn't be occupied. And so this looks something like that. Okay, and so now you can see why the sign makes such a big difference, because when epsilon minus mu is 0, the exponential becomes 1, and whether you're adding 1 so that you get a 2, or subtracting 1 so that you get a 0, has a huge effect on this occupation number. Okay, and then what can happen is if epsilon minus mu becomes negative, let's suppose that it's negative and we're at a very low temperature, so we're dividing by a small number. Then we have e to a large negative number, which makes the exponential vanish. And in that case, we have 1 over 0 plus 1, which is 1. And so over here is, maybe fix that. So if we double the height, this is 1 is over here. And so for large negative values of epsilon minus mu, we get 1. And then this has to smoothly connect with the rest of the curve. And so this is the Fermi-Dirac distribution, and so you never have in any given state more than one particle. Okay, so maybe we'll just make a note that proof that spin 1/2 particles have anti-symmetric wave functions and spin integer particles have symmetric wave functions is called, the proof of that is called spin statistics theorem. And I believe that that requires relativistic quantum mechanics. Okay, and so we're not going to do that. All right, so that's two ticks on our roadmap, the Pauli exclusion principle, and just writing down what these distribution functions look like. So I want to do a little bit more review of quantum mechanics, and we're going to recall the wave function for a particle in a 1D box or an infinite square well. And so the result was that this wave function had some coefficient, and then it was sine n pi x over L. And so I'll draw this. This A is just a normalization constant. Okay, so if we draw a square well, here's x, and our square well is going to go, and it's going to have a width L, let's say. And so I want to draw some of the wave functions that exist. If we had an infinite square well, that means that the potential goes to infinity outside the well, and the wave function will vanish. And so there's some boundary conditions. And if you recall, what the boundary conditions do is it requires that the wave functions have to vanish. And so this is going to be the so-called n=1 state. And over here, if we shift up a little bit, there's going to be n=2 state. And then if we shift up again, we're going to have an n=3 state, and so on. Okay, and so these are the wave functions that are going to satisfy our boundary conditions that the wave function has to vanish at x=0 and x=L for all the different states. So if we look at this, we could kind of see that there's a wavelength, or there's a period of oscillation. And so in the n=1 state, half a wavelength is equal to L, or λ1 is equal to 2L. In the n=2 state, λ2 is just equal to L. We get one full cycle. And in the n=3 state, we have a wavelength of 2L over 3, and you can continue in this way. In general, the nth state is going to have a wavelength of 2L over n. Okay, so let me also remind you of the energy of a particle in a particular state is given by the Hamiltonian operating on the wave function, and we're going to get an eigenvalue, which is the kinetic energy of our particle, multiplied by the wave function back again. Okay, so sometimes people put a little hat on the Hamiltonian to indicate that it's an operator, and for our system that we're considering, this operator is given by minus h bar squared over 2m times two derivatives with respect to x. And so this is the Hamiltonian. Okay, good. So what I'm going to do next is a useful quantity for us, we'll see soon, will be the so-called wave number, or k. And so we're going to define the wave number to be 2 pi over lambda n. And so we could even put a little subscript on there. And using lambda n is 2L over n, we could write this as pi n, or n pi, over L. And so then if we do that, we have inside of our wave function, we have n pi over L, and so we could write our wave function as a sine kx. Okay. Define the wave number such that our wave function can be written as a sine kx. Okay, I've dropped the subscript, but we'll just remember that the k values can take on a number of discrete values. Okay, so if we operate on our wave function, then what we get is minus h bar squared over 2m times 2 derivatives of a sine kx. So when we take the first derivative, we get k times a cos kx, and when we take the second derivative, we get minus a, and then we'll get back to sine kx, and we'll get another factor of k, so we get 2 factors of k coming out. And so if you do this derivative, you get h bar squared k squared over 2m times the wave function back again. And so that means this is our energy. E depends on k, and it's h bar squared k squared over 2m. And if you put in the value of k, n pi over L, this is n squared pi squared h bar squared over 2m L squared, where n can be positive integers. Okay, and so that's just a little review of our 1D infinite square well. So what I want to think about then is what happens if you do this in 3D? So by analogy, the wave function of a particle in a 3D box, let's say a cube of sides length L, is, well, we're just going to have the same restrictions in all 3 dimensions, and so we'll have to set up standing waves along all 3 of the axes. And so we'll have a standing wave condition along the x-axis and a standing wave condition along the y-axis and along the z-axis. Okay. And so using our definitions of the wave number k, we have sine kx, x, sine ky times y, and sine kz times z, where ki, like before, is this n pi over L, where the I subscript represents either x, y, or z. Okay, so we could write down our boundary conditions that this wave function satisfies. And the condition is that the wave function has to vanish when x, y, or z are equal to 0, or when x, y, or z is equal to L. And so you can see that's why you have to have the product, because if z is equal to L but x and y are not, we still require the wave function to vanish, and taking the product of these sine functions achieves that. Okay, so the Hamiltonian in this case is also similar. So in the 1D case, this is what we had, but now we also have to account for motion, kinetic energy associated with motion in the y and z directions. Okay. If you operate on our 3-dimensional wave function with this Hamiltonian, I'll leave it to you to confirm that what you're going to get is h bar squared over 2m and then you're going to have kx squared plus ky squared plus kz squared. And we can take these components, x, y, and z, and when you square them and add them up, what you get is the magnitude of the net k vector. So wave number, or k vector, is going to be k squared. The square of the magnitude is k squared, and that's kx squared plus ky squared plus kz squared. And then if you put in the values of kx, ky, and kz, this is equivalent to h bar squared times pi squared over 2ml squared. In the 1D case, we just had n squared, but now in the 3D case, we have also ny and nz, where now each of the three n values can take on any positive integer. Okay, good. So let's now think about what would happen if we have particles in a 3D box, and in one case, maybe we'll have a set of identical bosons, and then in another case, we'll have a set of identical fermions, and let's see what the difference in the behavior of these systems are. So let's consider a collection of non-interacting bosons confined to a 3D box in the t equals 0 ground state. Well, for bosons, if you're really at temperature equals 0 or very close to 0, then all of the particles are going to want to occupy the lowest possible state. In bosons, there's no restriction about having multiple identical particles in the same state, and so they all just go into the lowest ground state available. So all bosons go into the lowest energy state. And so the lowest energy state is all of the n values, nx, ny, and nz, go to 1. Okay, so therefore, for n identical non-interacting bosons, the system's ground state energy is, okay, so ground state energy, let's call that E0. So this is the total energy of the entire system. Every particle's in the ground state, and so nx squared is 1, and y squared is 1, and z squared is 1, and so we just get 3, and so we have 3 pi squared h bar squared over 2ml squared. So we have 3 pi squared h bar squared 2ml squared. That's the energy of each particle in the system, and so if there's n particles in the system, that would be the ground state energy of the system. Okay, so that's relatively easy. Let's think about what if we had n non-interacting fermions. And so we assume that they're all identical particles. So, for example, let's say like helium-3 atoms. Okay, So there's one little subtle point. So helium-3 has spin 1/2. And so there's also a spin part of the wave function that we haven't written down, and I'm not going to write down. But it turns out that the spin can be spin up or spin down. And so those correspond to a different quantum state. So what we can do is we can put two particles in each of the available states in our, say, our 1D square well, as long as one of the particles is spin up and the other one is spin down. Okay, so helium-3 has a spin 1/2, so we can put two helium-3 atoms in each state. One spin up and the other spin down. Okay, so in a 1D well, we would have something like this. Let me draw it over here. So there's an n equals 1 state and an n equals 2 state and a 3 state and 4 and 5 and so on. The n equals 1 state has an energy of pi squared h bar squared over 2ml squared. The n equals 2 state has 4 times that energy because there's an e squared. The n equals 3 state has 9 times that energy, and so on. Okay, so what we would end up doing is we would put one spin up particle in the n equals 1 state and one spin down particle. So we'd use 2 of our n particles in the n equals 1 state, and then the next one would have to go into the n equals 2 state. The fourth one would have to go also to n equals 2 state but have opposite spin of the third, and this would just continue like so until we used up all of our n particles. And you can see that the ground state energy is going to be quite a bit higher than it was for the boson system, because in the case of the bosons, we would put everything just in the n equals 1 state. And so you'd get n times E1. But if I add up this total system energy for the fermions, you know, the energy keeps going up and up and up and up when I have more and more particles. So if we have n particles, we would end up filling up to the n equals the number of particles divided by 2 state. So the highest occupied state is called the Fermi level. So in this diagram over here, if we had a system of where n was only equal to 8, then our highest filled state would be the n equals 4 state, and that would represent what we call the Fermi level. And so the Fermi energy is the energy of the highest occupied state. Okay, the Fermi energy is the energy of the highest occupied state at the Fermi level. So in the case that we've drawn for n equals 8, the Fermi energy would be E4, which would be 16 times E1. So in 1D, the Fermi energy is equal to n over 2 squared, the highest, so n over 2 is the highest occupied level, and then we have to square that, and then we get pi squared h bar squared over 2ml squared. Okay, So just remember then that that's not the energy of the system, that's just the energy of the highest occupied level. To get the system energy, we'd have to add up the energies of each of the individual particles. So 2 in the n equals 1 state, 2 in the n equals 2 state, and so on. So the question then is, what would be the Fermi energy if we had n identical fermions in a 3D box? So this is a useful question because this is like the conduction electrons, which are identical fermions, inside a block of metal. Okay, so let's think about this picture. So I'm going to try to draw something that's called, I'm going to call this K-space. And so we're going to have 3 axes. There's the Kx axis, the Ky axis, and the Kz axis. And what we're allowed to do is let's label quantum states. And so this would be like the nx equals 1, nx equals 2, nx equals 3 and 4 for ny and nz equals 0. And then there's, say, ny is equal to 1, and nx is equal to 1. ny is equal to 1, nx is 2, ny is 1, nx is 3, and so on. Okay, and then it gets hard to draw. Oh, sorry, I shouldn't have. N can't be 0. N has to start from 1 in our case. Okay, so sorry about that. Let's erase those ones. It gets hard to draw, but then we could have Kz is equal to 1. And we could draw these things. Okay, and what we could do is we could select any one little cube that exists in here. And so we'll draw a couple more. And there's a little cube that exists in here. And that cube occupies a volume in K space. So this plot is called the K-space plot. And so what we can say is, if we take one step in K, so let's remember the definition of K. Ki was, let's find it. I think it's way back here. Yeah, Ni pi over L. Ki was Ni pi over L. And so the volume of this little cube is pi over L cube is the volume of K space occupied by each state in the system. Okay, the cube has, I guess, 8 corners, and so, but it shares those corners with 8 other volumes in that space. So each state occupies this volume pi over L cubed. Okay, and if we were to think about filling up these energy levels one by one with particles, we'd put first a spin up and a spin down in the state where nx and ny and nz are all equal to 1. And then we would take the next highest energy level and then the next highest one and the next highest one, and we put 2 particles in all of these states. And what we're trying to do is we're trying to crowd as close as we can to the origin of these axes. And as you add more and more particles, what's going to happen is you're going to fill up the volume that represents 1/8 of a sphere. And then what we can do is we can define, let's say this touches the surface of the sphere. We can define a vector which we're going to call kf, and so that's the Fermi vector. And so kf is the Fermi wave vector. And so in words, what we've done is we fill the lowest energy states in this K-space one by one with two particles of opposite spin until we've used up all n particles. Okay, this process will form a, let's say we'll form 1/8 of a sphere, which we could call the Fermi sphere. Okay, so one thing we could do is we could look at the volume of this sphere. The volume of the 1/8 sphere is 1/8 of, so a sphere has a volume of 4/3 pi times the radius cubed. The radius of this sphere is kf, the Fermi wave vector. And so let's see, 1/8 times 4/3 is 1/3 times 1/2, so we get 1/6 of pi kf cubed. Okay, so the total volume of that space is 1/6 pi kf cubed, and then we said each state occupies a volume of pi over L cubed. So then if we wanted to know the number of states inside our Fermi sphere, we would take the total volume and divide by the volume per state. So the number of states inside the Fermi sphere is the volume of the sphere divided by the volume occupied per state. Okay, so the total volume is 1/6 pi kf cubed, and the volume per state is pi over L cubed. And so that ends up being L cubed, kf cubed, and then we have 1/6 pi squared, because we cancel one factor of pi. Okay, so that's the number of states inside our Fermi sphere. We know that we can put two particles per state, one spin up and one spin down, one spin up and one spin down. Therefore, we require, if we have n particles, then we need n over 2 states And the number of states in our Fermi sphere is L cubed kF cubed over 6 pi squared. And so we can solve for our Fermi wave vector. Kf cubed is then what? 6 divided by 2 is 3. We have a pi squared and an n over L cubed. Okay, so that's our Fermi wave vector. And we can say since E is equal to h bar squared k squared over 2m, then the Fermi energy, which is h bar squared times the Fermi wave vector squared over 2m, is h bar squared over 2m, and kf squared is going to be this 3 pi squared n over L cubed, and it would have to be to the 2/3. And so this is the Fermi energy of n identical fermions in a 3D box. So Fermi energy of identical fermions in 3D box. Okay, good. So I'm going to end about here. Let me just point out one thing that's important. An important point to remember when we discuss mixtures of helium-3 and helium-4. What our analysis has shown is that this Fermi energy is proportional to n to the 2/3. So it's a little bit slower than linear than n. If we were to plot this, the Fermi energy as a function of the number of particles, n to the 2/3 looks something like that. Okay? And so good, that's where we'll stop. So we've covered the Fermi energy for our 1D square well and for our 3D box. And we'll pick up somewhere along our roadmap the next time we meet. All right, thanks very much.